Hello everyone, thanks for coming. Today I'm going to do a review of our last week's lectures, numerical ordinary differential equations. So first, we do a review of ordinary differential equations. We are interested in the initial value problem, dy dt equals to f of t and y, given the initial value y0, and so for the solution at yt when t falls in the interval 0 to a. So if the right-hand side f is continuous, then the solution to the ordinary differential equation exists. If f is Lipschitz continuous on both variables t and y, then the solution is unique. So we are mainly interested in the case when the solution exists and is unique. In this case, how can we get a numerical approximation to the solution? So we talk about two Euler schemes. Given Ti equals to Ai divided by m that are equally distributed on the interval 0 to a, the forward Euler method approximates Yti plus 1 by Yti plus h fti Yti. The backward Euler method approximates Yti plus 1 by Yti plus h fti plus 1 Yti plus 1. So the backward Euler method cannot be solved explicitly because Yti plus 1 appears on both sides of this equation. So given those two Euler schemes, how can we evaluate the error? If we denote the ground truth solution at Ti as Yti and the numerical solution as Yi, then we define the local truncation error as, for the forward Euler method, as Di, which is Yti plus 1 minus Yti divided by h minus fti Yti. So this is the local truncation error for the forward Euler method. The global error is defined as T or Eti equals to Yti minus Yi. So we have this Euler propagation formula for the forward Euler method. The absolute value of Eti plus 1 can be bounded by the absolute value of Ei plus L times h. L is the Lipschitz constant of the function f times the absolute value Ei plus h times the absolute value of the local truncation error. So this is the error propagation for the forward Euler method. So there are some important concepts when we talk about whether the numerical ordinary differential equation solver will converge. Consistency. Consistency means that the local truncation error goes to 0 as the step size goes to 0. Stability. Stability means that for the ODE, y prime equals to lambda y, lambda smaller than 0, if the numerical solution will give us yi goes to 0 as ti goes to infinity, then the method is stable. That is to say, if the ground truth solution goes to 0, then the numerical solution also needs to go to 0. Convergence. If as the step size goes to 0, the global error Ei goes to 0 for any I, then the numerical ODE method is convergent. So briefly speaking, we can show that consistency plus stability implies convergence. Also, convergence implies consistency and stability. So for the Euler methods, for the ODE, y prime equals to lambda y, where lambda is smaller than 0. The forward Euler method requires that the absolute value of lambda times h is smaller than 2 in order for the method to be stable. Because if lambda times h is the absolute value of lambda times h is greater than 2, then the solution will blow up. The numerical solution will blow up while the ground truth solution will converge to 0. So for the backward Euler method, it is unconditionally stable. So thanks for listening.